Dear students, welcome back to our NPTEL course on analog electronic circuits. Myself Pradeep Mandal from ENEC department of IIT Kharagpur. So, we are going to continue our previous topic, namely the common emitter amplifier. We have started this topic in the previous class, and we are going to continue on the same thing. So, what are the plan we do have? It is in the previous class we have discussed about the CE amplifier with fixed bias, and today we will be going little detail of another kind of bias called self bias. And in the previous discussion we already have cleared that fixed bias, it is having some stability issue, particularly the operating point stability issue, which is resolved by this self biasing. That is what we will be discussing in detail. And then subsequently we will be discussing about the self biased CE amplifier and then its corresponding analysis, having two parts. One is the DC operating point analysis and then small signal analysis, which is eventually giving us small signal equivalent circuit of CE amplifier having self bias. And then subsequently we will be talking about the mapping of the small signal equivalent circuit of CE amplifier on a voltage amplifier, and then in typical voltage amplifier it is having three important parameters, how those parameters can be obtained in the small signal equivalent circuit. As a methodology we will be discussing as well as this example, and then subsequently we will be discussing about two numerical examples. So, under the numerical examples we will be having analysis for a given design. We will do the analysis to find the numerical value of gain and operating point, of course, and then we will be giving some design guidelines for achieving some performance of an amplifier. So, this is what we will be covering today. So, let us talk about the biasing scheme and then let me compare the two biasing scheme. So, as we have discussed that this is the fixed bias kind of circuit, and here what we have done, it is the base current, base terminal current, particularly the DC current IB, it is decided by the VCC and then VBE on and this RB. So, in fixed bias circuit the base current, it is well defined by the base resistor called RB, and then supply voltage minus base to emitter diode on voltage. So, once say this base current is defined and that is fixed, then the corresponding collector current of the transistor it can be obtained by simply multiplying this IB with the beta F of the transistor. So, what we have discussed that since IC it is a direct function of the beta F, there may be a situation in case if the beta of the transistor it is changing, then the collector current directly getting affected, and if the collector current is getting affected, the drop across this resistance, as a result the collector to emitter voltage of the transistor that may vary. So, we can say that operating point of the transistor it was getting heavily affected by variation of the beta of the transistor. In contrast to that, we are going to discuss about this circuit, which is referred as self bias, and in this self bias what we have, it is this emitter resistor we are connecting in series with emitter to the ground, and on the other hand at the base we prefer to give a DC voltage rather of course, we do not want this voltage should be ideally DC voltage, because we like to feed the signal here. But then the voltage here, DC voltage here, we want predominantly defined. In other words, we want this Thevenin equivalent resistance of this bias circuit should be as small as possible in terms of the bias stability. So, even if we consider practical value of VBB, RBB, it is much smaller than whatever RB we do have. So, we can say that the RBB in the self biased circuit, it is much smaller than the RB of the fixed bias circuit. So, we can say that even if say the base current is flowing through this circuit, IB it is flowing through this circuit, the drop across this RBB it is very small. As a result, we may say that this voltage it is approximately VBB. Now, once this voltage DC voltage it is remaining almost constant, then VBB minus the VC the base to emitter on voltage. So, VBB minus VBE on divided by the whatever this RE, that defines the current flow here. So, in other words, we can say that this emitter current IE in the self biased circuit, it is defined by this voltage difference and then divided by RE. So, if RIE it is independent, quote and unquote independent of this the beta of the transistor. So, naturally the collector current it is also quote and unquote independent of the beta F. So, in this circuit, in the self bias circuit, in contrast to the fixed bias, the emitter current VBB minus VBE on divided by RE. So, that is this current, and we can approximate, if the beta is very high, we can approximate that the collector current is very close to that. So, in this expression, since beta is not there, so we can say that the collector current is quote and unquote independent of beta of the transistor. So, that is the main purpose here. In other words, based on our requirement, if we fix the value of this RE and then VBB, assuming that RBB it is very small, then the collector current it is almost decided. As a result, the DC operating point of the transistor it is almost fixed. So, that is the main advantage here. Let us see what may be the analysis of this circuit to compare these two circuits performance. In fact, if you see it carefully, what can be seen here, that VBB we may consider as a special case, it is VCC, and RBB it is similar to RB. However, as I said that in this circuit RBB it is much smaller than RB, and that can be obtained because we are adding this emitter resistor RE. So, in contrast to this circuit where emitter is connected to ground. So, we do have the flexibility to change this voltage, and predominantly we can say that this circuit is more like a voltage bias rather than current bias what we are seeing in the fixed circuit. But nevertheless, we may consider that this circuit is more generalized, and the self biased circuit it may be treated as, in general it may be treated as a special case where you may say that RE it is going to 0, and then VBB is going to be equal to VCC and whatever the RB is there. So, to compare the expression of the collector current in the two circuits, probably we can analyze this circuit and we can find the expression of IC and then we can probably through equation we can compare the collector current expression in the two circuits, namely in the fixed bias circuit, the collector current, it will be having a lot of dependency on the beta of the transistor, whereas for cell bias circuit the dependency it will be less. So let us see the analysis of this circuit here. So in the next slide we are going to analyze this circuit in detail. So here we do have the same circuit we have discussed so far. So we do have the main transistor which is biased by VBB and then RB, and at the emitter we do have RE resistor, and of course we do have the signal, it is coming through this capacitor, and then at the output we are observing through the capacitor. And also of course we do have the resistor at the collector terminal. Now if we want to know the DC operating point stability for this circuit, we can concentrate the DC part, ignoring the signal part. So if we consider this loop at the base to emitter, what we can get, the expression of the VBB equals to VBE on plus the drop across this resistance RBB, which is RBB multiplied by IB, plus the drop across the resistance RE, which is RE multiplied by the emitter current. And the emitter current we are writing in terms of base current, which is beta times of IB plus the IB. So this is the emitter current. So the drop across this resistance is RE into the emitter current. Now if we rearrange this equation to find the expression of IB in terms of VBB and beta F, so from this equation we can get the expression of IB equals to VBB minus BBE divided by RBB plus 1 plus beta into RE. Now from that we can find the expression of the collector current. Collector current is beta times the IB. So this expression, it is same as this one, except we do have the multiplication factor beta F. So this is the expression of the collector current. Now to find the sensitivity of this collector current on the beta variation, what we can do, we can take partial derivative of this equation with respect to beta. So if we say that dou IC divided by dou beta, assuming that the this factor it is having practically no dependency on the beta variation. In fact, strictly speaking, beta is having influence on the VBE, but if I consider change in VBB minus VBE, practically you can consider the variation is very small. So with this assumption, considering this factor, it is quote and unquote independent of the beta, so we can take this factor out, and rest of the things we can take the partial derivative. So as you can see that this factor, it is coming in the form of square here in the denominator, and then in the numerator we do have beta. So if you take the derivative of beta first and then multiply with this, so we are getting RBB plus 1 plus beta into RE, and then minus beta into, if you take whatever the derivative of the denominator part with respect to beta F, that means it is RE. So that gives us in the numerator, which is RBB plus RE. So this is the sensitivity of the collector current with respect to beta variation. Now if you see this equation, this numerator part and in the denominator part, if I consider only one factor, this ratio is nothing but the expression of IB current, which is IC divided by beta. So if I replace one factor here and the numerator, what we are getting here, it is IC divided by beta of the transistor. And then of course we do have the remaining factor RBB plus RE divided by RBB plus 1 plus beta into RE. So this equation, further if we try to get meaning out of it, more engineering meaning of that, what you can rewrite this equation by considering this factor into the left side. So instead of dou IC, we are writing here it is change in IC by IC, which means fractional change in collector current divided by fractional change in beta. So this ratio, if I consider its expression, it is RBB plus RE in the numerator, and in the denominator we do have RBB plus 1 plus beta into RE. Now interestingly, the same equation can be used to find the sensitivity of the common emitter amplifier operating point on beta variation for both fixed bias. So if I consider fixed bias, we can consider RE equals to 0. So RE, if I take it 0 for fixed bias, and then what we are getting here, it is this expression, it is becoming RBB divided by RBB. So that means then the sensitivity, it is becoming 1, which means that whatever the percentage variation we do have in beta, same amount of percentage variation it is expected in the collector current. On the other hand, if I consider say the emitter degenerated bias by putting this RE non-zero, and then if I consider that this part it is much higher than RBB, in that case if I consider RB is not equal to, sorry, RE is having some finite value, so not is equal to 0, then this expression it becomes and also if I consider this part, it is very high compared to RBB, so this is becoming RBB plus RE divided by 1 plus beta into RE. And if I further simplify by considering this RE, it is higher than RBB, so that is becoming equal to 1 by 1 plus beta, which means that whatever the fractional change you do have in beta, that is getting reduced by this factor, almost 1 by beta times the factor, to get it reflected in the variation, fractional variation in collector current. So that is what the theoretical basis, that if you put the emitter register, and if you consider that RBB it is much smaller than 1 plus beta into RE, and further to that, if I consider that RBB it is also less than RE, then we do get this advantage. And typically for cell bias, what we do, it is we do take RBB is less than or equal to 1/10 of 1 plus beta into RE to get meaningful effect on the bias point stability by placing this RE. So now let's look into the next slide. So what we have here, it is we do have the same circuit we have discussed. We do have VVB. Now if I consider say this loop, this low, then we can say VBB equals to VB on plus drop across this resistance, which is RBB multiplied by IB, plus the drop across this emitter resistor RE, and the drop here, it is of course the resistance multiplied by the emitter current IE, and IE, it is 1 plus beta of the transistor times IB. So, this is the drop across this RE. So, if we rearrange this equation to get the expression of IB by taking this IB left side, and what we are getting here, it is IB equals to VBB minus VB1 divided by RBB plus 1 plus beta into RE. Note that here there is no approximation. So, here as I said that if we consider two special cases, the same equation will be helping us to find the expression of the base current. Now, if I am having this base current, we can get the collector current by multiplying with beta of the transistor. So, the expression of the collector current is given here. It is same as this part along with multiplying with this beta. Now, if we like to see what will be the variation of this collector current with variation of beta, we can take partial derivative of this equation with respect to beta, and if we assume that this part, this VBB on, it is quote and unquote independent, quote and unquote independent of beta f, though it is not theoretically exactly correct, but practically that is quite consistent, particularly since we are not looking at VBE independently, rather we are observing VBB minus VB1. So, even if it is having some variation, but if I consider VBB minus VB1 variation with respect to beta, that can be ignored. So, if I assume that this part is remaining constant, and then if I take partial derivative with this IC with respect to beta f, what we are getting here, it is VBB minus VB on divided by this denominator. Note that here this part, it is IB. So, the expression of this IB, it has been used here to make a to get a nice form. But in this form, what you can say, if we further analyze, if I take the change in collector current divided by collector current, that means fractional change in collector current divided by change in beta divided by beta. So, we can say that fractional change in collector current divided by fractional change in beta, that is having this expression, which is VBB minus VB on divided by RBB plus 1 plus beta into RE. So, if we assume that this part it is much higher than this part. So, if I consider this RBB, it is much smaller, then we can say that this is VBB minus VBE on. So, divided by 1 plus beta into RE. Now, due to this 1 plus beta coming in the denominator, this is since it is inversely proportional with beta f under this condition, of course, then we can say that sensitivity of the collector current change with respect to beta f, it will be quite small. On the other hand, the same equation, if I consider RE equals to 0, so if I consider this is on the other hand, if I consider for the fixed bias, where this RE equals to 0 for fixed bias, and for that the dependency of the collector current with respect to beta f, or fractional change in collector current divided by fractional change in beta f, it is only this one. So, as a result, you can see that this part it will be quite significant compared to this one, which is the fixed bias case. So, or directly maybe you can use this equation and then you can compare the two circuits, namely yeah. So, we do have we can replace this part by IB, and then we can say that it is having strong dependency on beta f. So, anyway, so what we like to say here, it is we like to bias this circuit in terms of voltage, and we like to place this emitter resistor to get the better stability of the operating point, particularly if we are changing the transistor by another one having different beta, or maybe due to the thermal runaway, if the beta is changing, this circuit it will be having a better stability. Now, what is the practical circuit? Let us see. So, this is what the practical circuit you can see, that instead of having independent voltage at the bias voltage at the base, what we have here, it is potential divider from VCC by this R1 and R2. So, the voltage coming here, if I consider Thevenin equivalent voltage source of this one along with the VCC, what we can get is VBB, it becomes VCC multiplied by R2 divided by R1 plus R2, and then Thevenin equivalent resistance RBB, what we have drawn in the previous circuit. RBB, it is parallel connection of this R1 and R2, or you can say R1 multiplied by R2 divided by R1 plus R2. So, that is the expression of RBB. So, as I said that this is the practical implementation of this cell bias, and of course, we do have the RE part, emitter resistor connected there. So, yeah, so the typically this circuit is quite popular, and then we do use this emitter resistor to avoid the thermal runaway problem or the dependency of the quiescent point on the beta. Now, in this circuit, similar to fixed bias, the voltage at this point, it is having a DC voltage defined by this R1 and R2 and then VCC. Practically, this VVB, it is defining this DC voltage, and then on top of that we are feeding the AC signal through this coupling capacitor. So, we do have the AC signal riding over there. So, we do have the AC signal riding over this one. So, the voltage here, it is having a DC voltage, and then on top of that we do have the signal. Now, at the output, similar to the previous case, it is also having a DC voltage level. So, this DC voltage level at this point, particularly at this point, it is having the drop across this RE plus whatever the VCE voltage you do have, or we may say that VCC minus the drop across this resistance, that gives the DC voltage. So, we can say this DC voltage, it is VCC minus RC into IC, and then to get the IC, we have discussed that once this voltage it is given here, then that minus VB on. So, that divided by RE, that gives the emitter current, and that actually it gives the approximately the collector current. So, IC, you may say that this is approximately equal to VBB minus VBE on and divided by this RE. So, that is the emitter current. So, approximately you can consider that. So, that is how we are getting DC voltage, and once we have the AC signal at the base coming from the signal source, and naturally this is also having the small signal current IC along with the DC current, and as a result it is also producing a drop across this resistance, and hence we do have the signal at the output. Only thing is that since we are subtracting from the DC voltage this drop across the RC, we are subtracting from the VCC. So, the signal here it is having 180-degree phase difference with respect to whatever the signal we do have. Okay. So, in this circuit, let me go a little detail of analyzing the input part and the output part, namely the input port. So, if I consider input port is this one DC wise, in addition to that we do have the signal, and the output port we do have on the other hand consist of the collector resistor, transistor, and also this emitter resistor. So, you need to see that this emitter resistor, it is part of the input port as well as the output port, So, in the input port, while we will be analyzing, we need to be careful whenever we will be talking about the IB current, we need to see how much the current actually it is flowing. In fact, the current here it is not only IB it is flowing through this one, but also the IC. So, whenever we are writing say IB here, the current here it is 1 plus beta times IB. So, that we need to be careful. So, and then of course, then we will be talking about the small signal thing. So, let us see the input port circuit what we are discussing here along with the signal part. So, at the input port what we have here it is so this is the circuit we are talking about. Let me mark it here. So, at the input port we are talking about this one. So, we do have the R1 and R2 coming in parallel to give us the RBB. So, RBB which is parallel connection of the R1 and R2, and then VBB it is the voltage, Thevenin equivalent voltage coming from VCC and R1 and R2 together. So, we do have VBB, it is having the expression earlier we have discussed about that, VCC multiplied by R2 divided by R1 plus R2. So, then out of the transistor from base to emitter we do have the base emitter diode, and then at the emitter node. So, this is the base node and this is the emitter node, and at the emitter node we are having this emitter resistor. Now, at the emitter of course, we do have the additional current flowing into this. So, whenever we will be talking about IB it is flowing here, we need to consider that IC also, which is beta times IB. As a result, the current flowing through this part it is 1 plus beta times IB. So, if it is DC current, we will be talking about 1 plus beta F times IB. Now, if I consider, if I replace this diode, base emitter diode by its equivalent circuit shown here. So, which is a parallel connection of the VB on voltage and then small r pi, and again at this node we need to consider that collector current is coming here, which is beta times IB. So, now if we analyze this circuit, what we can get here, it is the IB. So, rather VBB minus VBE on equals to IB times RBB plus R pi and then plus IB multiplied by 1 plus beta times RE. So, here we may or may not be able to I need to consider this is RBB. Yeah. So, in this case we may or may not be able to ignore this R pi in this case. So, we may have to consider this entire portion, but if we consider say drop across these two resistances, since RBB it is much smaller than the RE part, then typically compared to this part we may ignore this part. So, we may say that IB equals to VBB minus VBE on divided by 1 plus beta f into RE. In fact, in our previous analysis we have ignored this part compared to this one, but even if you consider this whole thing, these two together, it can be ignored compared to this part. So, as a result, what is the expression of the current IB we are getting? It is VBB minus VB1 divided by 1 plus beta into RE. So, large signal analysis if we do, then we can find the corresponding base current. Whenever we will be talking about some numerical example, we will see that this current will be very small, and once we get this beta IB, then the collector current it is IC equals to beta f into IB. So, that we can approximate that VBB minus VBE on divided by 1 plus beta f into RE and then whole thing multiplied by beta f. So, we may ignore this one part and then we may cancel this part and this part. So, that gives us the collector current, it is independent of beta f. So, that is what again we are converging to the same point. So, that is what we do. The input port we do this large signal analysis. Only thing, as I said, that we need to be careful that this RE it is also taking the current of the output port. Now, from this circuit after getting the large signal current, probably we can do the small signal analysis. So, I do have different slide for that. In fact, the same circuit we are drawing here, but what we are talking about, we are going to talk about the small signal analysis. So, once we have this entire circuit and we like to see what will be the corresponding small signal equivalent circuit. equivalent circuit. What you have to do here, we have to make it AC ground. We have to drop this part and then we have to short it. So, what we have it is, we do have a signal source shorted to the base node. So, this is the base node, this is of course the emitter node, and then we do have the AC ground, and then we can keep this R pi, and then we do have the RE, but again we need to be careful that we also have the collector current because, to be considered. So, if I say collector current is IC, that is also flowing through this RE. So, if we have say this current, we do have say small IB. So, this collector current it is beta times beta naught times IB. So, as a result, the current flowing through this circuit it is 1 plus beta times IB into RE. So, that is the drop. So, probably you may drop this current source, you may drop this part, and then instead you may simply say that this resistor it is getting multiplied by 1 plus beta naught of the transistor. And so, then we may you may forget about this part, you may say that the resistance is getting increased. So, that is what normally it is followed, but whatever the way you feel, we need to be careful that we need to consider this collector current, or probably the emitter resistor we need to consider its amplified version of the emitter resistor. Now, this Vs it is coming here and it is going to the base terminal. Note that this is emitter terminal. So, obviously, Vs it is not same as VBE as it was for fixed bias. It is rather having a voltage drop here, which is called base to emitter voltage, different from this Vs. Now, let us look into the output side. So, whenever we will be talking about the small signal equivalent circuit, we must consider this analysis. And so, while we will be going to the small signal equivalent circuit for the entire emitter amplifier, common emitter amplifier, then we have to consider this circuit. So, we will be coming back, but for the time being let me consider the output port. And again, for this output port what we have, it is emitter resistor, it is common. So, let me go to the So, here again we do have the large signal and more small signal notion, and here we do have the actual circuit, and at this point we do have the voltage shown here, and we are going to talk about this circuit along with this DC decoupling capacitor. So, what we have at the collector, we do have the RC collector resistor connected to the VCC, and then collector to emitter we do have the current, and if it is, of course, it is having a DC current I capital C plus in case if it is having small signal small IC also, but whatever it is, this entire current it is flowing through this emitter resistor, and in addition to that at this node the base current is also coming. However, this base current it is small compared to this collector current. So, we may or may not ignore this part that we can see, but this is what the output port. And once to find the DC operating point, once a IC it is known by analyzing the input port, then you can say that that current is flowing here, and the DC voltage coming here, which is VCC minus RC multiplied by and this I capital C. So, that is the DC voltage coming here. So, the voltage at the output node or the collector node rather, it is VCC minus this drop. So, this is VCC minus RC into I capital C. Now, once you obtain the DC voltage here, let us look into the small signal part, and similar to the input port, here again for small signal, what are the things you will be doing? It is this terminal will be considering AC ground. So, this is AC ground, and here this DC part it will be removed. So, though it is having total current is I capital C plus small I C, but this will be dropped, and whatever the current it will be flowing through this one, it is only small I C. So, this is also small I C, and the corresponding capacitor here, of course, it will be getting shorted. So, whatever the voltage, small signal voltage you are getting, that will be called small signal output voltage, while we are dropping this DC part. So, if I draw the small signal equivalent circuit, we do have the RC connected to AC ground, and then we do have the small signal current, small IC, and then at the emitter we do have the RE. Maybe we can think of the base current coming here, IB, and then at the output we can say this is the open circuit output signal. So, this IC, of course, we may be having different expression. One of them, it is IC equals to transconductance of the transistor multiplied by base to emitter voltage, and since this is ideal current source, so we may to find this output voltage, we may prefer to see how much the drop across this resistor is appearing, while small signal current IC it is flowing. So, the output voltage at this point, output rather signal, it is minus IC into RC, which is, of course, this is equal to minus GM into VBE into RC. So, while we will be combining this small signal equivalent circuit at the output port and small signal equivalent circuit at the input port, then we can get the combined small signal equivalent circuit. So, let us see what we are going to get here. Yes. So, we do have this small signal equivalent circuit shown here, where now if you see at the collector side, we are making AC ground. First thing, the capacitor here we are shorting, so that is what we are doing, and then the collector current, it is having only the small signal collector current, small IC, which is GM times VB, and the VB, it is the voltage drop between the base terminal and the emitter terminal. Okay. So, this is the voltage drop across, you may say that this is drop across R pi. So, of course, we are giving the signal here. So, the voltage coming at this point in this circuit, since we are eliminating the DC, we do have plus and minus kind of signal, and the output here we are removing the DC. So, we are getting the only the signal part. And in this illustration, as I said that the signal here, it is in opposite phase of the input signal. That is because of the voltage coming here, it is minus RC into GM into VBE. Now, if you see here, this VBE, of course, it is not same as Vs. So, this is not Vs. So, since the VBE it is not same as Vs, it is rather only a part of it, we need to do the detailed analysis of this circuit. Now, we are going to take a small break, but just to after we come back, we need to find what will be the relationship between this VBE and the Vs. So, VBE as function of Vs, and while we will be doing this, we may use this important relation that this IC, we may say that this is GM into VBE, or we may say that this is beta times IB. Anyway, we will come back and we will be having little more discussion to find the output voltage.